So number 3, one slide in 5 minutes, we are going to talk about how the vector search is computed in a database. For more context, it's better to watch the previous videos. Before diving into the technical details, let me ask you a question. Imagine you are working for a big company where you have access to all employees. Now, if you want to find a specific employee based on some criteria, let's say, for example, an associate in data science, you have 2 options. You can go through all the employees one by one and ask them if they match the criteria. Or you can start at the top of the hierarchy and ask the general manager, who would redirect you to the VP of engineering, who would redirect you to the director of data, and so on until you get to your right person. By following the second approach, you have leveraged the hierarchy to optimize your search and save time. Now, let's get to the subject. In the previous example, we have indexed our data, and now we have our index vectors. If we zoom in our vector database, we have something like this. Many vectors sparsely distributed in space. Now, when a user sends in a query in a text format, it gets translated into a vector using the embedded model. And now we have a vector query that needs to find its similar match. But what do we mean exactly by the similar match in the sense of vector search? This is somewhat philosophical. And some people would define the similarity as the Euclidean distance between 2 vectors, while others would use the cosine between the angles to compute this distance. Since it's subjective, vector databases are generally flexible when it comes to this, and they allow you to select the similarity method on the query when you're writing your query. Now that we have settled this debate, we face another challenge. How do we efficiently navigate the vector space? And this is more of an engineering problem. Because the simplest way is to brute force comparing the query to every index vector. But you have guessed it, this is not optimal. Instead, we can skip some vectors by letting the vectors themselves guide us through this approach. And this approach is called the NSW, or Navigable Small World. Here's how it works. The query vector starts by comparing itself to a random entry point. The entry points suggest another vector that is closer to the query. This process continues until there is no closer vector left. However, this assumes that all the vectors are on the same level. In reality, the entry point may be far in terms of its connections. So to optimize this, we add some hierarchy layers. Think of it this way. The layer 1 contains all the capital of the worlds, or the capital cities of the worlds. The layer 2 contains the representative capitals per continent. And the layer 3 contains 1 capital representative per planet. So now when searching for the nearest capital, your first check is the nearest planet, and then the nearest continent, so that you can end up to the nearest country. This is one of the most widely used approximate nearest neighborhood algorithms. But why is it called approximate? Well, because the selection of representatives, vectors in this hierarchy or in those layers, is done using the probabilistic distribution of the space. We have covered a lot: vector spaces, layers, embeddings. But how is this all start? This is another topic for another 5 minutes.